Yeah, so hello everybody. Yeah, I know it's late, so hopefully I'll be able to keep people awake. So I'm going to talk about simple and efficient learning with dynamic neural networks. It's heavily based on a toolkit called DyNet that I've been developing with Chris Dyer and also Yoav Goldberg. We have stickers. If you want a sticker, they're on the front table over there. They're on the front table over there. Get one as you walk out or come up to me. I can give you one as well. So because this is a large theme of this machine learning school here is language, I think it's important to talk about things that are specifically interesting to language. Of course, a lot of the stuff I'm going to talk about you can use in this time you can use in any application, but specifically if you're trying to deal with language, neural networks have given us a lot of new tools to do this, and I'm sure a lot of people have heard about neural networks and deep learning as a way to process images, speech, text. And particularly for text, and also for other applications like reinforcement learning, where you want to learn how to do something or other things, you end up wanting to use networks with complicated structure, and I'll show you some examples of this. Another thing is that nobody likes taking lots and lots of time to turn their idea into code. So ideally, we would want to go from idea to code quickly so we can try out lots of interesting new things and get results. So I'm going to give a simple example of a task that we would like to do. I've given versions of this tutorial before. Just coincidentally, it happens to be the exact same task that you just did in the lab. It's about sentiment, but we have a slightly different bent on this task. So for sentiment, we have I hate this movie, I love this movie, and I don't hate this movie. And we want to say whether each one of them is very good, neutral, bad, or very bad, like this. So the first one, what is the answer here? Yeah, very bad, I think. What about the second one? Very good. Okay, what about the third one? Neutral. Yeah, it's a little bit more difficult, but let's call it neutral. So the interesting thing here is that we can do processing of this text and kind of guess. Humans obviously are able to do it. But there's also some complexities, which is this one here has the word hate in it, but the word hate is not necessarily indicating that it's very bad if it's negated. And it's not necessarily indicating that it's very good if it's negated either. So another thing is that basically text or language has structure, and you can also think of structure like this parse structure here. And like Yoav Goldberg talked about yesterday, parsing allows you to discover this structure, and we might want to use something like this in our predictions if we think it would be intuitively useful. So the idea is that we want to be able to design neural networks that perform a task like this and maybe even take advantage of the fact that we have something like structure here. So what is necessary for neural network training? This is, we talked about this before, but just to reiterate, we need to define what we want to compute. We want to add data to it, add training data to it. We calculate the result. So if we're just doing test time, then we calculate the result to use it to do something. Or if we're training, we calculate gradients and then update parameters. And the example that we saw before in Theano is using a paradigm called static graphs. So basically the idea is at the very beginning of training, you define the computation that you want to do. So at the very beginning of training, you say, this is the function that I want to calculate. Then for each data point, you add data. You do forward and backward calculation, and you do a parameter update. This is clear? Okay, so these have a few advantages. So One of the advantages of this method is that it can be, you can kind of optimize your calculation at definition time. So you may have noticed when you're using Theano, right when you do your first calculation using this computation, it takes a little while to compile the graph and do some optimization and turn it into machine code. It's also, when you're doing neural networks, often you want to do things on GPUs, for example. And if you already know what computation you're going to be doing, you can do things like queuing up some data to send to the GPU, et cetera. So in general, if you already know what you're going to do, static graphs have the advantage that you can kind of optimize things so they move efficiently. The disadvantage here, there's two big disadvantages. Actually, maybe I'll talk about the second one first. So the bad, one of the disadvantages of this paradigm is that in order to express all the various things that you want to do within your computation graph, you need to have this big complicated API. So for example, not this time, but next time, you're going to learn in Theano that there's a thing called a scan function. And the scan function is basically, it's a for loop. It's like a for loop that goes over each element in a list. But you can't use a for loop in Theano. You have to use the scan function. Similarly, if you want to do an if statement, there are ways you can do that, but you can't just write an if statement in Python. And this is true for TensorFlow as well. Another thing that makes it very difficult is because we can't use for loops, we can't use if statements, we can't use recursive functions, it makes it very difficult to implement something that's a little bit more complicated than, say, taking in a fixed size image and predicting the output. And this is why if you want to use something like trees or graphs or complicated flow control, it makes it more difficult. So paradigm number 2 is using dynamic graphs, and that's what I'm going to talk about this time. There are a number of toolkits out there to use them. Chainer and DyNet are toolkits that have been around since around maybe 2015 or so. And then PyTorch is a new one that a lot of people have been interested in that just came out this year. And the difference here is what you're doing is for each data point, you basically define your computation for each data point. You can do this using standard Python operators like if statements, for statements, or recursive functions or whatever. And then you add data, perform the forward pass, backward pass, update, et cetera. So the main difference here is whether this definition of the graph is inside your for loop, you do it for every data point, or whether you do it at the beginning. So these have a lot of advantages. The API is much closer to Python and in C++. So you don't need to learn a lot of new things. It may, you just program in Python and use your standard mathematical operations. It's also easy to implement nets with varying structure. I'll show you some code examples later that basically show something that looks rather complicated can actually be implemented quite easily. One of the disadvantages is the advantage of the static graph framework is you can go in and do optimization. This is more difficult in dynamic frameworks, but it's still possible. And I'll show you an example of something that we just introduced to DyNet at the end of the presentation, which allows you to code in a natural way and do this optimization at the same time. It's also a little bit harder to schedule data transfer, etc. You can't, it's not trivial to use queuing operations and stuff like that. But I think mainly, especially if you're not a neural network expert, if you're going to learn a new framework at the moment, the first selling point is the really big selling point here. So you can just program in a way that's very natural to you, and I highly recommend this. So DyNet itself is a toolkit. You can download it here and take a look at it. Its features are that it's a dynamic graph toolkit implemented in C++. You can use it from C++, Python, Scala, and Java, and very soon Haskell. So if you are a fan of kind of crazy programming languages, Haskell may be the way to go. We don't have this yet, but if you want to be on the mailing list, just tell me. It's also very fast on CPU. So for example, if you don't want to do a big, if you want to do quick prototyping, you want to run it on your own computer and run lots of experiments, running on CPU is often better than, is often easier to do than GPU. It also has similar support to other toolkits on GPUs, so you can use GPUs as well. And maybe one of the big selling points that isn't really available in other toolkits is its easy implementation of mini-batching. So even if you have very complicated network structures, you want to try complicated things, you can do easy implementation of mini-batching. And that's one of the things that I'll talk about at the end today. So are there any questions so far? OK, so I'll go ahead. So next I'm going to give some programming examples of how you would do this. And I showed a website at the very beginning, and I think you sent a mail to everybody. So you should have an email in your inbox. You can go there and you can follow along and try to run things if you would like. But I'm going to give some examples of how we solve this sentiment analysis task, which is a very simple task in NLP compared to parsing, for example, but might give a good illustration of the kind of things you can do. So first, let's try this with something called bag of words. So bag of words is not normally what people think of as a neural network, but you can solve it with DyNet, so let's try. So what we're going to do is we're going to, for every word in our sentence, we're going to look up a vector. And this vector will have 5 elements. It will have one element that is the score of very bad, one element that is the score of bad, one element that is the score of neutral, et cetera, good, very good. And we will do this for all of the words in our sentence. We'll also have something called a bias vector. So the idea of a bias vector, you might have heard already, but basically this is if we have lots of very good and lots of very bad examples in our training database, we'll want the probability, or we'll want the possibility of getting very good or very bad to be higher, so we'll give them a higher score in this bias vector here. Of course, this is learned along with all the other parameters, but that's what it's useful for. Then we add all of them together, and this gives us a vector of scores. So we have 5 scores, one for each label that we're trying to predict. Then we take the softmax function, so we exponentiate the scores and normalize, so they add up to 1, and we get probabilities. So in order to implement this in DyNet, this is about maybe 30 lines of code, plus or minus a few for reading in your data. So at the beginning of training, what we do is we define a model. So we start DyNet, we define a model. So this is where we'll be storing our parameters. We also have a trainer. So in this case, we'll use a trainer that will be updating our parameters given our gradients. And we'll use one called Atom, because this is one that tends to work pretty quickly and relatively well. And then we define the model. So the first 2, these will be the same for all of the models that I'm talking about today. The second 2, this will vary from model to model. And in DyNet, we have, so here's our strategy for training. So in DyNet, we have 2 different types of parameters. Basically, one of them is what I'm calling here regular parameters. They're just vectors or matrices or tensors of floats, of floating point numbers that we use to calculate something. So we have a parameter. So here, our bias vector, this is just 5 numbers that we use to bias our predictions. And for here, n tags, just assume that's equal to 5. We also have things called lookup parameters. So we have one vector for each word. Here, this has a vector for each word in our vocabulary. So n words is the size of our vocabulary. If we have 2,000 words in our training corpus, then the size will be 2,000. then n tags is the number of tags also, or is the size of the vector, basically. So this would be 5. So the next thing we need to do, this is saying calculating the network. Actually, it should probably say defining the network. So what we're doing is we get words. So these are the words in our particular sentence that we want to calculate the score for. We call this die.renewCG thing here. So die.renewCG basically creates a new computation graph for the example that we're trying to process now. So if you remember at the beginning of the talk, I said one of the main differences between Theano and this is for every training example, we redefine our computation graph. So in this case, the first line there is saying, OK, start with a new computation graph. Then we add the parameters to our computation graph for all our normal parameters. So basically what this is doing is we have these parameters that are defined in our model. We move those parameters into the computation graph so we can use them as part of the computation graph. Now, this is where we're actually calculating the score. So for every word in the input sequence, we look up its word embedding by passing this ID. So sorry, I should mention the things in words here. These are integer IDs for all of the words. So assume that we already have converted our sentence into integer IDs. Then we look up that word, and we create a list of these word embeddings. And then the esum over here is just summing these vectors together. So this is written in regular Python. It's using a list comprehension, which is kind of difficult Python. I'm sorry, I just realized maybe I shouldn't have used a list comprehension in my examples. But this is a standard feature of Python that you can use to turn one list into another list. And it kind of shows that in DyNet you can do this, where you couldn't do this in other toolkits easily, or in static graph toolkits easily. Then at the end, we additionally add our bias vector, and then we return this here. So that's how we calculate the scores. And then with scores, we'll want to do one of two things. The first thing that we'll want to do is train our model. The second thing that we'll want to do is test our model and actually make predictions. So for training, we first, for every set of words and a tag in our training corpus, we calculate the scores using the function that we previously defined. Then based on this, we calculate our log function. Were the cross-entropy log function, the cross-entropy loss functions covered earlier this time? So this is a complicated name for the cross-entropy loss function. The reason why it's called this is because the cross-entropy loss function, you basically do it by taking a softmax, taking the log of the softmax, making it negative, and then picking the example that you want. But just think of it as the cross-entropy loss function here. So now we have a loss here. And we then take the value of the loss and add it to this training loss, which we use to aggregate our whole loss here. So one kind of feature of DyNet that's different from other dynamic graph toolkits, it's different from PyTorch and Chainer, is we're using something called lazy evaluation. So have people heard of lazy evaluation in the programming language sense? OK, a fair number of hands. But basically the idea is we don't actually evaluate the value of until it's requested or until it's necessary. So up until the previous line here, we actually haven't done any computation. We've just defined the computation that we want to run. And then on this line is when we actually go through and run all of our computation. And this is actually important because it allows us to do kind of on-the-fly optimization of our graphs, which is the thing at the end of the talk. But I'll explain this in a little bit more detail later. Finally, we do backward computation. We calculate our gradients, and we update our parameters. And at the end, of course, we'll want to print our loss value, et cetera. Then at test time, we do something very similar. We take in our words, and we calculate the scores. We can get a NumPy array from the values here. So this runs computation and returns it as a NumPy array. And then we use the NumPy function argmax to get the maximum value of this, which is our prediction. And then we compare it to our true tag. And if it's correct, then we add 1 to our score. So this will allow us to calculate accuracy. So that's basically it. There's a little bit of boilerplate code about reading in the data, et cetera. But now we can take a look and see it actually run. So actually, first, let me show you what the data looks like, just so you can take a look at this. Our training data here is a label. So this 3 means good, 4 means very good, 2 means neutral, et cetera. And then we have a sentence on the right side, like this. So this will be the data that we're reading in for the training testing, et cetera. And then we run this. And so just to walk through briefly one more time. We have all our imports like you always do in a Python program. This is boilerplate code to read in the corpus and turn it into word sentence tag values. I won't go through the details. You can take a look if you want. But basically, what this results in is we now. Oh, sorry. And then we use this to read in the data set. What this results in is now we have the first element in our training corpus is something where we have words in the first, like a list of words in the first one, and then we have a label in the second one. So then we can use this to train our model. Then we define the model, like I mentioned before. We add the parameters. We define our calculate score function, like I talked about before. And then we have our big training loop where we do 100 iterations of training or something like this. So overall, I think this program is, I don't know, maybe less than 100 lines, but you can train a bag of words classifier like this. So let's let it run. And we can see that it's running over the training corpus in maybe 0.4 seconds on my computer. And we can see our accuracy is going up a little bit, 34, 35. This is the fun part of machine learning where you watch your accuracy go up while your model is training. And actually, this one's really slow, so maybe it tops out off at around 37% or something like that. So that's the general. This is our first model in DyNet, basically. And I will leave full screen. Are there any questions about this so far? No? OK. I'll try to do something a little bit more interesting next. So for the next one.
Sorry, I have a question.
Yeah, sure.
So what is the main advantage of using this framework as opposed to having to build everything in Python from scratch?
So like what level do you mean? Do you mean like coding all the equations for your neural network in Python?
No, I just don't appreciate why this is a neat idea.
What would be the alternative?
I don't know, using Tano or something?
OK, so the advantage of this over Theano one advantage that you can't really see here in this example, but you will be able to see in the later examples, is here I'm using a Python list comprehension, which is a standard programming construct in Python. And you might want to use something like this when you're programming. And this is not trivial to do in Theano. You need to learn the way to do it in Theano. Similarly, for a for loop, for an if statement, or a recursive function, for example, these are all things that either you need to learn the syntax in Theano or you just can't do in Theano. So I think that's the main advantage for this. Yeah. Any other questions? OK, so I'll move on to the next one. Also on CPU, it's quite a bit faster than Theano, if that means anything as well. So the next one I'll do is a continuous bag of words. In the interest of time, I might actually skip the implementation details of the continuous bag of words and go on to the next one, which is similar. But we could also think of a thing where basically instead of looking up a vector that said whether this word was very good, good, neutral, et cetera, we could just look up a vector, a random vector for this, or not a random vector, but a vector that represents this word, and add them together, and then multiply this by some matrix, and add a bias to get our scores. So what this is doing is basically saying, instead of remembering good, very good, neutral, et cetera for each word, we're remembering features for each word. So maybe the first feature in this vector could be something like, is this word a word about movies? Is this word a negative word? Sorry, a negation. So is it like not or didn't or something like that? The third one here might be, is this word a word that's generally positive? So this is kind of the bread and butter of neural networks in natural language processing. We basically express words as vectors of numbers. And then we do manipulations of these expressed words as vectors of numbers. And in this case, we're simply multiplying it by a weight matrix. This is a little bit less interesting, but you can try it and take a look at the results. When this actually becomes interesting and gives you better expressive power than you would have had before is when we actually make this into a neural network. So let's say we take this I hate this movie. We have features for each of the words in this movie. And then we run this through a nonlinearity. So this is like the nonlinearity that you learned about in the neural networks. Maybe we multiply it by a weight matrix and add a bias vector and take a hyperbolic tangent. And then we do it again. We do it for another layer. And then we multiply this by a weight matrix, add the bias, and get some scores. So why would we want to do this? Why is this a good idea for sentiment analysis? Well, as I said before, maybe the first feature of this word is whether this is a word about movies or not. And maybe the second feature of the word is whether this is something saying this is a long, like length, like long or something like that. Actually, maybe the movie example is not quite as good. Let's talk about apartments and cell phones. So it's much easier in this context to understand because if you have an apartment and you have a cell phone, you want a big apartment. That's a good thing. And you want a small cell phone in general. Maybe some people might want a big cell phone, but in general, you don't want it. You would prefer a small one. So if that's the case, just looking at the word small doesn't give you very much information about whether it's a good trait of the thing that you're talking about. But if you know that it's an apartment that you're talking about and the word small appears, then that's a good indication that it's a good thing. If you're talking about an apartment and the word small appears, it's a good indication it's a bad thing. And neural networks, they learn these feature. They have the ability to learn feature combinations, as I'm sure you heard this morning. So by basically extracting the features of the words and then running them through these linearities, we can learn more complicated interactions between the words like that. And this model actually works remarkably well for sentence classification if you tune the parameters correctly and do a few tricks. And there are papers on this. So let's take a look at what this would look like in DyNet. So we have this. And the beginning stuff is all the same. Now, because we need to define a model with hidden layers, etc. Now we have our word embedding model, which is the thing that takes in a word and turns it into a vector. This is a lookup parameter. Then we have weight parameters, the weight matrix and the bias vector for each of our layers, and these are appropriately sized. So the first one takes in something that's the size of the word embedding and outputs something the size of the hidden layer. The second one takes in something that's the size of the hidden layer and outputs something the size of the hidden layer. And then in the final thing here, we basically do the transformation of this into our scores. Or we have parameters to do this transformation into our scores. And our calculation function basically looks like this. What we do is we renew our computation graph. We add up all of the word embeddings. Then for each weight matrix and bias vector, we do the multiplication like this and add the bias and take the tan H and get our new hidden state. And then we do the multiplication to get our score. So it's basically exactly the same as the graph that I showed you before. It'd be exactly the same as the equations that you have in a paper. So our training loop is exactly the same as before. So the only thing we've changed is our definition of our parameters and our function to calculate the scores. So let's run this. And of course, it's a little bit slower because now we're doing more complicated calculations. But it's maybe it's 0.97 seconds, so it's maybe twice as slow. And now we have a score of 40% accuracy. So our score went up a little bit over the bag of words model, which is good. Usually when you add complexity to your model, you would hope that your scores get better. Of course, this doesn't happen a lot of the time, but if you're lucky, then it does. So that's so this is the same. And here we're still in the realm of things that are relatively easy to implement in static graph toolkits, because all of these things are things that people have thought about and tried to implement easily, or tried to make it easy to implement. So now I'm going to get a little bit ahead of myself because I'm sure Chris is going to talk about this tomorrow. But there's this large class of more complicated models, and this is where something like DyNet becomes much, it starts to become much easier to use than other toolkits. So let's say we have a model that uses this thing called a bi-directional LSTM. If you know what this is, then that's great. If you don't know what this is, you'll know tomorrow. But basically, the first thing we do is we look up our word vectors like we always do. And then we have this, this vector here that is basically the state of our LSTM at the beginning of our sentence, or the state of our recurrent neural network at the beginning of the sentence. And this starts out as all zeros, basically. Then we take the input and this vector, and we put it into a function called the LSTM, which will be explained tomorrow, and it calculates a new vector. Then we do it again, taking the state after the first word, and then we calculate a new vector. So basically, we do this till the end of the sentence. And what this means is that every time, basically, we're reading a new word, we're updating our state based on that information from the new word. And when we get to the end of the sentence, we should have all the information that was in the sentence, or all the relevant information that was in the sentence encoded in this vector here. So the important thing is basically just that the LSTM is a recursive function like this. And we can also do it in the opposite direction where we start at the end of the sentence and gradually calculate forward like this. So now what we have is we have basically two sets of vectors. The first set, the very last vector in this set is the one that resulted from reading the sentence forward. The very last vector in the second set is the one that resulted from reading the sentence backwards. And then we can concatenate them together. And then we can use that as input to predict our sentiment. So, this is a model that we can make. Because one of the main use cases for DyNet is models that use LSTMs, for example, the parsing work that you all have talked about yesterday, we have made it relatively easy to use these. So in model definition time, we have something called LSTM builder, where basically you define the number of layers in your LSTM. You define the size of the input to the LSTM, which is called the embedding size here, because it's often a word embedding. We take the hidden size, which is the size of the vector that the LSTM is going to compute. And then at training or testing time, we get the initial state. So this is basically the zero vector that I was talking about. We calculate for every word embedding in our word embedding vector, we call the add input function. So this adds the input to the LSTM. So this is like updating our state, like I said before. And then at the very end, we can use this output function to get the output of this. So just to show it in action in the entire sentiment analysis system, we do the initialization the same. Now, instead of having the hidden layers that we had before, instead of having the multiple hidden layers we had before in our multi-layer perceptron example, now we have these LSTM builders that will read things in a forward and backward way. Our calculate scores function is a little bit more difficult, or a little bit longer. It's not really that much more difficult. So basically what we do is we first look up the word embeddings. We get the first, we get the initial state. And then for each word embedding, we walk through in this order. Then for backwards, we also get the initial state. And we do exactly the same thing, but instead we use the Python function reversed, which reverses the order of the word embeddings. So this is all we need to do it backwards. And this is what you already know from your Python programming class or whatever, if you use Python. Then we take the final output of both. We concatenate them together. And then we calculate our score like we did before. So this is another example. We're using a for loop. We're using the reversed function of Python. So it's quite straightforward to do this. And then we run our training. And we wait, and we wait, and we wait, because because LSTMs are quite a bit more complicated than the stuff we've done before. I should also mention in the meantime that LSTMs are really great at a lot of things. One thing they're not super great at is reading whole sentences and then predicting a tag at the end. So you'll see, OK, it's not doing that badly. I expected our score to be a little bit lower. But anyway, so it took about 16 seconds to run through the entire corpus with this now. And we have another iteration. And now it's evaluating. Oh, 43. Pretty good. We exceeded our previous state of the art using the using the simple model that just added words together. So yeah, sorry, go ahead.
What is the biggest bottleneck in that case, for example? Because I noticed that you're using Python 4.
Uh-huh.
And for example, PyTorch doesn't require Python 4. It has a cell that you can do it as
Right.
just like that. Or
So that That is true. I'd say the biggest bottleneck is just running an LSTM over 40,000 sentences is going to take a certain amount of time, especially if you're not doing it on a GPU. I'd say 16 seconds for parsing the entire corpus is actually pretty good. But with regards to what you were talking about, where PyTorch has a function that you can run over the entire thing, DyNet also has a function like that. I actually didn't use that function on purpose to show that you don't have to use it. It has a function called transduce, where if you do want to use it, you can. And that will make things a single function call instead of writing a for loop, for example. So, yeah.
Is the for loop that is making it slow, or is it?
No, I don't think it would be any. It would be significantly faster if you did. It just takes a little bit of time to run through the entire corpus. So one thing I should mention is this corpus is I don't know several thousand sentences. So doing it in 0.4 seconds is kind of like the exception rather than like what you should be expecting most of the time. So if you have a model with a certain level of complexity on the CPU, it's probably going to take about this amount of time. So I should mention the data is from something called the Stanford Sentiment Tree Bank, which is the standard data for kind of sentiment analysis. So, you know, it will take a little bit of time to run your models on it, but I think this shows that it's very reasonable to kind of hack up something and run it on the CPU and test things out. Okay, so now let's do something a little bit more interesting. Let's say we have something that is, let's say we have something that's a little bit more complicated. So I mentioned at the very beginning that we have structure in language, and that's what Yoav makes his living doing, discovering this structure from language. And there are a number of proposals to use this in a way that's conducive to, or that will help your task accuracy in neural networks. So one of them is the tree-structured RNN, or LSTM. And basically the idea here is I should have drawn a parse tree first. But basically, if we have a parse tree, a phrase structure parse tree, this movie will be a single phrase, hate this movie will be another phrase, and then I hate this movie will be the top phrase. So what these models do is basically they take in two words, they run them through some sort of transformation, and use this to calculate a vector. But when they do this, when they calculate this recursively, what they're doing is they're doing it in the same structure that we have our tree structure. And in the end, once we go all the way to the top of the tree structure, we'll have something at our root node. And then we multiply this by a weight matrix and add a bias to get scores. So why would we want to do this? One example of why following this structure might be useful is, for example, if we have something like don't. So don't takes in, don't modifies a phrase. So we have, or not. Not would be a better example. So if you have the best movie that I've ever seen, that's a single phrase. That's a very, very positive phrase. But then you have something like not the best movie I've ever seen. So suddenly that very positive phrase becomes something much less positive. And if we can model this appropriately according to the structure of the sentences, then this will give us better accuracy. So this was, or may give us better accuracy. It gives you better accuracy for some tasks and doesn't give as good accuracy for other tasks, or doesn't help for other tasks. But anyway, so let's try to do something like this. There was a really simple example of this called the recursive neural network, or tree-structured neural network. And so how would we do this? In a static graph toolkit like Theano or TensorFlow, this is often given as the example of the thing that's very difficult to do in that framework. In Theano, I don't think it's possible to do it efficiently. In TensorFlow, they have a variety of methods that supposedly make it possible, but it's very difficult to code in that way. So the way it looks in DyNet, this is a little bit more complicated than the other examples, but basically the idea is we have a weight matrix that takes in 2 hidden vectors and outputs a single hidden vector. And so it takes in 2 vectors for smaller phrases and combines them into the vector for a larger phrase. And then we have a thing that we can use to look up words. We assume that we already have our tree structure, so we have some separate tree structure parsing code that creates a Python variable that's basically this hierarchical tree structured thing. So if we're in a leaf of the tree, basically we look up the vector for that particular leaf. So this first part is this part here. Then, sorry, then you can kind of skip this. This is some extra stuff that actually probably isn't necessary if we coded it in a slightly different way. But then the next thing is basically we find the child of tree of the left node. We find the child of the right node. We take this matrix, then we concatenate together these 2 things, and then we multiply this by a matrix and take the tanh to calculate our representation. So the important thing here, I guess, is this is a recursive function. So you can see here we're calling this function itself to calculate the children, the things for the children. So this is something that's very easy to write in Python, but it's very difficult to write in another graph language. So because of this, this is all you need. These 15 lines are all you need to implement a paper that was one of the state-of-the-art papers in this a couple years ago. If you want to implement something that's a little bit more complicated and was the state-of-the-art maybe 1 year ago, then this is a thing called a tree LSTM. It's basically like a more complicated version of the tree of the recursive neural network, but also you can implement this as you would like as well. And you can see basically these equations are taken directly from the tree LSTM paper. You can just grab them and implement things according to the equations. So let's try to run this. And we will run this. Our calculate score function is actually now extremely simple now that we have this tree RNN builder or tree LSTM builder. We just calculate the representation for the root node, and then we calculate our score. So all of this work is done within in the recursive function. And then our training loop is exactly the same, and now we run this. This is actually, I'm doing the tree LSTM version because the tree RNN version doesn't work quite as well. But let's see. So I think this is a little bit faster than the LSTMs. No, okay, it's about the same. So, so then this is training. You get an accuracy of 35. I think this improves to about the same accuracy as LSTM. But while we're letting it train, maybe this is the end of the coding examples. So are there any questions about this? Yeah. So the biggest difference with PyTorch is it's kind of the things that I listed at the very beginning of the slides. PyTorch is only Python. This works in C++, Java, Scala, other things. PyTorch is not as fast on the CPU. So if you want to run things on the CPU, then it's better. On the GPU, it is about the same or a little bit faster for some things. These kind of more complicated things, you actually don't get a big benefit from running on the GPU because it's hard to do stuff like mini-batching, which I'll talk about next time, unless you use some functionality in DyNet. The last thing about DyNet that's an advantage is that DyNet has automatic mini-batching capability, which is what I'm going to talk about next, to make things with complicated networks a lot better. The advantage of PyTorch is if you're trying to do like image processing, for example, there's many more examples for image processing if you're not doing NLP-related stuff. It also has a slightly larger user base. Like DyNet has a lot of examples, but PyTorch has more examples that you can use. I'd say those are the biggest differences. Other people might have things. So this was slightly worse than just using an LSTM. So I think none of these are state-of-the-art results. I think the state-of-the-art was like 47 or something like this on this task. So all of these would need parameter tuning, but basically you can see that they're doing okay here. So let me stop this, and I will now talk about the most, maybe the biggest advantage of DyNet over other dynamic graph toolkits. But basically, one of the big efficiency tricks that you, I think, learned at the end of the lab this morning was mini-batching. Did you cover that? So basically, just to reiterate, the reason why we want to do mini-batching is on modern hardware, doing 10 operations of size 1 is much slower than doing 1 operation of size 10. So mini-batching, it combines together smaller operations into one big one and basically makes speed improvements. So just as a little quiz, let's say you want to add 2 numbers together. But you want to do it over and over again. So you have, let's say, a big vector of numbers and another big vector of numbers, and you want to add them together. If you write a for loop over all of the numbers, then it will take, 1 operation for addition, then 1 operation for your for loop, et cetera. But if you, or maybe a couple operations for your for loop, et cetera. But if you do this, in a more intelligent way, does anybody know how many operations you can do in a single instruction on modern Intel processors?
5.
What was that? 5? I think it's more than 5. It's 16, is it?
16.
Yeah.
It depends on the size.
Depends on the size. Yeah. But basically, there are things called single instruction multiple data operations, which are things where you take a big vector of floats, another big vector of floats, and you send it to the processor. And basically, it goes through, and it does blocks of these operations at the same time, where it takes a single instruction to do 16, or it depends on the size of the float, for example. But in addition, things like matrix multiplies are much, much faster if you do a single big matrix multiply versus a bunch of small ones. So without mini-batching, basically what it looks like is this. You're doing your weight matrix times input vector plus a bias. And you're doing this for 3 different examples. But what we do instead when we're doing mini-batching is we take all of these vectors, we stick them together into one big matrix, and then we take this B vector here. And we don't actually expand it in memory, but we do something that makes it look like we're expanding it in memory called broadcasting, where basically this turns into a matrix where each column is equal to B. And if we do something like this, we can take our 3 independent operations and combine them into one, or 3 independent sets of operations and combine them into one bigger operation. So this is great. This is especially important on GPUs, where GPUs will run through these big operations in no time at all. Even on CPUs, it gives you huge bonuses in speed. So there are a couple ways to do this. You can do this manually, which is what is done in most other toolkits. So the way you do this in DyNet is a little bit different than what you do in other toolkits. Basically, in DyNet, you only worry about batching on the input and output parts, and then everything else in the middle, the mini batching part is completely transparent, and you just code like you were coding for a single example. So we have some examples here. If we have our non-mini batched classification example, basically we look up a word 1, we look up word 2, we concatenate them together, multiply them by a weight matrix, and then add a bias vector. And then we do pick neg log softmax to calculate our loss function. So this is just doing one thing at a time. When we do mini batching, basically what we do is we have a list of the first word and second word, first word and second word, first word and second word for multiple training examples, and then we have a list of labels. And then instead of calling the lookup function, we call up the lookup batch function, where we pass a batch worth of IDs. We also do this for number 2. And then the interesting thing here is I renamed the variables, so it's a little bit different. But basically, this line number 5 here is exactly the same. There are no differences here. And this is true no matter how complicated the network in between goes. And then when you calculate your loss, you also have to pass in the list of labels instead. So this is good, but when you start trying to do things with more complicated structures, like we have words that are split into various granularities, or if we have phrases where each phrase, yeah, sorry, go ahead.
Sorry, about the last.
Yeah, sure.
So, out of curiosity, I mean, for this mini batch stuff, how TensorFlow deal with it? Because my understanding is the implementation is always in terms of matrix instead of on vector, right? So basically, the row is always the number of data point in each batch.
So yeah.
I didn't see the big difference here. Maybe you can.
So the difference is that you have to do so the row is always the batch. Here the batch, so you basically need to increase your indices by 1. If you want to take the actual row, you have to take the first element or the second element, and then if you want to do something like I don't know, where dimensions are important, like transposing, you need to make sure that you keep track of the batch dimension, et cetera. So the idea here is that you could take your non-mini batched code and run it exactly as is without any changes on things. This is a little bit easier than TensorFlow once you get used to it. It's not a huge amount easier, except in some kind of corner cases, in which case it is. But yeah, so maybe the more interesting thing, which I'll try to finish up because it's getting late, but let's say we have more complicated things like the trees that we talked about before. In this case, it becomes extremely difficult to do something like this because if you're just looking at a sequence of words, you can do things like make the sequence lengths the same and do padding and masking and various things like that. And by doing that, what you basically do is you make sure that every time you can look up the same number of lists of words, or you can look up the same number of words. But when you get to something like this, it's basically impossible to fit all of the sentences in your mini batch into something that's the same shape, and that's a requirement if you want to do mini batching manually. So the DyNet has something called automatic mini batching, which basically allows you to not even worry about this at all. So the idea here is, let's say we want to run an RNN over 3 input sequences of different lengths and then predict something at the end. So what we do is basically we just call a for loop over all 3 of these sentences, calculate them independently, and create a graph, combine their losses together, and then run this, and DyNet will automatically find the parts that can be calculated at the same time. So it will automatically discover that nodes in blue are ready to be executed, and then these nodes can be grouped together using batch operations. Like this. And you'll notice that it didn't batch together everything. For example, the final one in the length 4 sentence, the final one in the length 4 sentence is done separately than all the others because there are no other operations to do in the other sentences, but it will automatically basically do this for you. This is also implemented in TensorFlow, but we were talking before about this TensorFlow fold thing, and basically you need to learn a new functional programming language to use this within TensorFlow. Within DyNet, basically, it's as simple as I just mentioned. You write a for loop, iterate over all of your instances, and do this. So this is extremely useful if you want to do something that's a little bit more complicated, where mini-batching is a pain. Even if mini-batching is possible in your instance, it's often the source of a lot of the complexity in your implementation, padding things together, et cetera. So I think this is an attractive alternative. So yeah, this is the summary. And just to give some results, so we have a paper on this if you're interested, but basically the example on the very top is something that is an easily mini-batchable, a problem where it's easy to manually do mini-batching. And if you look at the top row, this is not doing mini-batching. It takes maybe 200 milliseconds per sentence. But if we use our automatic mini-batching, which are the second and third rows, it reduces this to be much lower. The left side is on the CPU, the right side is on the GPU. And we compared it with manual mini-batching, and the automatic mini-batching is a little bit slower. There's some overhead in getting this automatic mini-batching to work on the computational side, like DyNet has to do some work. But they're pretty similar, like to the point where you might just want to forget about doing mini-batching yourself and let the engine do it for you. I should mention that the top one is like an ideal scenario where like everything can be mini-batched together. We also tried it on some non-ideal scenarios, like the Bi-LSTM thing that I talked about here, the Bi-LSTM thing with an additional character level model that you run to compute based on the characters. We ran it on the tree LSTM, and we also ran it on a transition-based parsing thing like what Yoav talked about yesterday. And on all of these, basically, this automatic mini-batching makes it anywhere between 3 to 10 times faster, I guess. And especially on GPU, it gets quite a bit faster. So yeah, so that's the entirety of my talk. So if this sounded interesting, go here, try out the code examples, download DyNet. If you have any questions, send an issue on GitHub. We try to answer promptly, but that happens maybe 50% of the time or 80% of the time. But we do try to answer everything, so we'll be happy to help. Yeah.
In the previous slide.
Yeah, sure.
In the previous slides, what's the with manual, without manual?
Okay, yeah, so the with manual is when you do manual mini-batching. So you can turn on both manual mini-batching and automatic mini-batching. So the idea is you know how to do manual mini-batching, but there are some things that you might have missed. So in this example, we had manually mini-batched the like LSTM operations for each time step. We had manually mini-batched the softmax for each time step, but the softmax is across time steps, and the word embedding lookups were done separately for each time step. which is kind of a natural way to do things. You treat each time step separately. And in this case, the automatic mini batching went in and batched those together as well. So we got additional improvements over even the manually mini batch thing. Yeah.
So does it compare to bucketing or something like that?
To what?
Bucketing, mini batching, similar sized examples.
Oh no. So the top one, all of the ones are of the same length. So basically, the idea is there are some operations that you batch together manually. But even after you've done that, even in a relatively smart implementation, there might be things that you didn't realize could be mini-batched together. So for example, the softmax operations across time steps, we were doing them independently, but actually they could be combined together. So that's why it's a little bit faster here. But in the canonical implementation, that's how I would do it. So yeah.
Hi, thank you very much for your talk. My favorite thing about TensorFlow is the TensorBoard and all the tools that are around it. Do you have something similar, or maybe bindings to TensorBoard?
So TensorBoard, that's actually something we're trying to create an example for, but it's not difficult to do using a library called, using various libraries like PyCrayon. So there's a library called PyCrayon that you can basically use to send data to TensorBoard. So we're working on an example for that now, but we don't have one at the moment. But if you try DyNet out and would like to try that, we'd be happy to take a pull request, for example. Yeah.
Okay, thank you.
Okay. There is just an observation that the comparison between the CPU and GPU, whether we can see that at most the GPU is four times faster than CPU, and on average it's only 2 times faster, right? From this result. Okay, very interesting.
Yeah, well, so there's 2 things I can say about. One is DyNet is very fast on CPU compared to other libraries. So if you're used to being slow on CPU, it will be quite a bit faster with DyNet. The second thing is these are, except for maybe this one, or most of these are things where mini batching would be difficult, and when mini batching is difficult, GPUs don't give big speed improvements. So yeah. Anything else? Okay, I'm happy to take individual questions afterwards. So thanks a lot. Oh. And don't forget your stickers.